is that number 14. And what we ran into in class is there is a way the textbook shows you on there, and it's long and lugubrious. There's an alternative, and I was exploring it with you guys. On Friday, I was looking through it in class and ran into the issue of here's the big idea. When you graph this particular function, it has a vertical tangent at x equals 0. And so when you try and implement the arc length formula, when you go to take the derivative of this, it's undefined at one of the bounds, 0. So we think, oh man, I can't do this. Well, sometimes the solution is to take a function with the vertical tangent. If you use the inverse function, it essentially turns it on its side, and so that vertical tangent becomes a horizontal tangent, and you can do it. Well, by traditional methods, one of the ways I tried in class was to do implicit differentiation. What I need is dx dy. Okay, so if I do dx dy, you can get dx dy from just taking the derivative with respect to y of our given expression, we call it y equals, and then get dx dy. But for whatever reason, that particular solution also is undefined at 0, which was baffling, and we found a reason for that. I contacted some colleagues up in Minnesota, and we went back and forth for a while, and we both had the same conundrum, like, why are these things equal? One's defined, one isn't. And we have a solution, but it's a little bit too lugubrious for this particular recording. So here is the quick route to fixing it, and following, if you didn't follow the textbook's route to solution, which many of you did, and you're all the better for it. If you take a look at this, I went through and just went ahead and took it the textbook method, but I thought I'd throw in some details about what on earth they're doing. The deal is they took the expression and they said, hey, look at that x to the 2/3. That's twice as big as x to the 1/3. That's a quadratic. And if you have a power of x that is twice as big as another power of x that's in your expression, you can work with this as a quadratic, and you can solve it with the quadratic formula. Do you know the quadratic formula, remember, is for finding roots of a quadratic function, you have to have it equal to 0 for this to work. So if you set the whole thing equal to 0, you get minus y as your last term. And since x is the variable, minus y is just some random constant at the end. It's your c value in the whole ABC that you need for the quadratic formula. So if you plug it into the quadratic formula, check this out. As you go along here, the big deal is that minus y is the c that goes in the formula, and that's what allows you to solve this thing. So here's x, and by the way, x cubed is your base power of x, as opposed to, because that's what's being doubled, x cubed, I'm sorry, x to the 1/3, I'm saying cubed, but x to the 1/3, if you double that, you get x to the 2/3. That's what we're seeing in our expression. So when you solve the quadratic, you're getting x to the 1/3, as opposed to regular old x. And then if you take and cube both sides, there's the one I wanted, after simplifying a little bit, this is the expression you get. So there's your x function. It can be graphed. That's the thing is, though, is there's two parts of it, right? Plus or minus. It's actually we call it piecewise function if you actually graphed it. Now I went in here and I've graphed half of it. So here is in green here. Let me take that, turn everything off. There's your green function. If I do minus inside here, it graphs the other chunk of what's the inverse function. This is only half of the inverse function. And if I do the other half, now I can actually just take our regular expression and just graph its inverse. It looks just like this. And so the method for getting the inverse and doing dx dy, there's a lot of thinking that goes on in there. We found something cool, but in the meantime, there you go. Here's our inverse function. Do you notice I took out the y's and I did an f of x function? That is meat for convenience of graphing. So I know that's a y in what we solved for in our expression. Let me bring that up again. And I just use x's because when you're graphing, I'm using GeoGebra here again. And when I want to graph that particular thing, you might as well just change it to y and x just for graphing purposes. And so I did, and here it is. That's the inverse half of it because there's another piece out there. To continue, the next thing we need, but that's just to turn the function on its side. What I really need is the derivative with respect to dx dy would be the, kind of your standard derivative of the inverse function. That's one way to think about it. And that dx dy, so if I take the derivative of this x function with respect to y, is a big chain rule. 3 comes out front, inside stays unchanged. Take it to the power of 2. Now I have to take the derivative of that inside. And if you'll notice that if you split it up, the -6/8 is a constant, so I can just derivative of that's nothing. But then I'm doing the derivative of that radical 30x plus 16y over 8. I'm thinking that is 1/8 radical 36 plus 16y. So here's what I got. And then if I take the derivative of the radical, I get 1/2 out front with my 1/8, which is 1/16. And then I take all that to the negative 1/2 power, what's inside there. So this is all to the negative 1/2 power now. That's not the end of it, right? Derivative of the inside. It has an inside too, which is 16. The derivative of 36 plus 16y is 16. And those 16s then cancel. And that's it. There's our derivative, our dx dy. That's nasty looking. Well, that's what I need to put in there. Now, I went and checked it, double-checked it with GeoGebra, something I want to start bringing up more and more in class. But check this out. Here's my expression up top here, f of x. I took the derivative using their lovely computer-operated derivative function, and it gives me this expression. I thought, that doesn't look like mine. So I did my derivative as we just wrote it with some simplification. And I said, were they really the same? Well, I graphed them against each other. And I said, okay, let's see if they're the same. Here's what they gave in red. Here's what I have in blue. They match. And so that's an assurance that, okay, they just have some simplifying in there that doesn't match mine. So I always like that when you get something and you want to check a computer derivative if Wolfram Alpha spits something out. If you want to know if they're the same, just graph them against each other. And then, in the end, what I wanted to do was my expression. The whole thing is the integral of 1 plus dx dy squared, and that's when I plug it in there. The big deal is the bounds change. We're also doing dy terms, and to get the y bounds, you actually have to put 0 and 1, what you have from your x bounds, into the function, and get your y bounds in respect to that. So I put it 0 in, I get 0. If I put in 1, I get out 10, and those are my y bounds I plugged in there. So I went ahead down here, did an integral. And the way you type these in, I can actually type it for you if you like. It's kind of fun to watch. I'll go ahead and delete this and do it again. But if you take integral, if you type int, and you choose the option where it's a function and start x and end x, that means a definite integral. What I'm trying to do is do the integral of the square root of, and I have an option for square root, 1 plus my derivative. Now I did mine by hand. I like mine, so I'm going to do g of x. So I'm going to 1 plus g, and you can just call it g in this, which is also cool, g squared. And then if you, to the right, tab out, tab takes you to the next lower bound, 0 to 10, and there's our integral. Plug it in, 10.071. It graphs the area of that thing, which is not useful right now. But that's going to be our answer, 10.071. It gives me the arc length. Turned it sideways, it was defined. Now 0 is not a problem in this fraction. Put a 0 in here and you just get 1 over the square root of 36, 1/6, and this is all just fine. So in this situation, it works. Standard, implicitly, it doesn't quite work, which is goofy. I'm going to type in 10.071 so you can see it. By the way, this is for a particular student of ours who needed this particular solution, so I'll let them know that I helped them out. But the rest of you, if you need it, just call me up, or I'm sorry, email me up, and I'll let that go. 10.071, hit enter, and it likes it. And sorry, I don't have it up on there so they can get it, but it totally gets that. Let me know if you have questions about it.